about electric fields. Quickity splits here. Ah, come on. Yeah, why not? Electric fields. Okay. A lot of this is review. There's two types of charge. Okay, positive and negative. And positive is carried by protons. And negative is carried by electrons. And from chemistry class, you know that the nucleus of atoms are positive, and the little wee electrons zipping around somewhere far away from that positive central core are negative. Okay, same amount of charge in each. Okay, one is positive and one is negative. How do we know? Well, there's some evidence for it. So if we take something like a plastic ruler and we rub that with a piece of fur, there will be an exchange of charge. Okay, so before we do this, there's always an equal number of protons and electrons, hence the object is not charged. If we rub it with a dissimilar material, we'll say some electrons leave the ruler and you end up with this scenario. Now remember, this was neutral at the beginning first, but 2 electrons went over here. So now we are deficient 2 electrons. So we have an area on here of positive charge. Okay? This has to be an insulator, because if it's not an insulator, charge can flow, and if you're holding this, electrons will flow out of your hand and ground out the charge, and you will not be left with a charge. Now, the electrons had to go somewhere, and so extra electrons came into here and is now charged negatively, right? 2 negatives, the 2 positives here. There is a conservation of charge. In other words, no charge is created or destroyed. It's just moved from one point to another. That should make sense, because in the universe, as far as we know anyway, there's the same number of protons and electrons, or the same number of positive and negative charges. Are you with me so far? Okay. Now, if I take something that is positively charged, this is now capable of exerting a force on other charged objects. So what we say is, in a space around here, in a field around here, a force is felt by other charged objects. So if I were to take a little wee test charge, and I were to place it in the vicinity of this large positively charged object, it would experience a force. So we call this a force field or an electric field. And the force acting on this positive charge would always point away. So we diagram this field as a whole bunch of little arrows pointing out from this object. Okay? So this is an important thing. Okay? We diagram fields, electric fields I should say, electric fields, using a positive test charge. Okay, so wherever we put the test charge, okay, this line is showing what force would be felt. No matter where I put this thing, it's going to always point away. If this changes to a negative charge, okay, now my positive test charge is always going to point towards. Okay, so far so good? So if you were to now imagine that you had 2 of these charges nearby each other, right? Well, opposites attract, right? So let's just put that down somewhere. Opposite charges attract. And that's because their fields interact with each other, okay? Like charges repel. And all charged objects attract neutrals. That's because neutrals are made of charge, okay? And those charges can sort of move around inside the neutrals. So even though they're not fully charged, they can become partially charged enough to attract to a larger field, okay? Now, if I put my test charge right in the middle, this is what would happen, right? The force would always be to the right. If I put it here, it would first repel away, but as it got more and more distant, it would start to experience force from here, and you get this. So your fields for positive with negative nearby start to do this kind of a thing. And you get this sort of pattern, right? Now, this isn't to say that anything like actually physical that you can view exists here. All it's saying is that wherever I put my test charge, the force acting on it will be the sum of its repulsion from the positive and its attraction to the negative. So if I put it in all these different places, okay, the force experienced is in the direction of one of these field lines. Okay, so if I take a positive charge and I put it anywhere in here, it's in the direction of these field lines. What if I take a negative charge and put it in here? What would happen? What would change about this if I flipped it to being a negative charge? What would happen to the force on it? It would just flip directions, right? If all of a sudden this became a negative charge, it would be repelled away and it would zip along that line away from here, okay? And if this were changed to negative, it would just be attracted towards here, so we would just get the opposite effect. Okay, and last but not least, what if we have two like charges? Well, we'll go with positives. They would have their field lines push outward, but when they encountered the other one's field lines, they would essentially cancel out in the middle there. Okay, so right down the middle between these two is an area where the fields have canceled out. There's no field, there's no net force, right? There's an exact equal force from either side. We point in opposite directions, so you get that. And if these were switched to negatives, we would just take the arrowheads and point them the other way. All right, so now we're going to talk about how we deal with measuring these types of fields, okay? So the first value we're going to talk about is this, 6.24 times 10 to the power of 18. Does anybody know what that number represents? Well, yeah, what this is it is the number of electrons or protons, okay, in 1 coulomb of charge. So basically what we're saying here is this is an amount of charge, right? Equivalent to the amount of charge on 6.24 times 10 to the 18 electrons or protons, okay? What that also means is that one electron or one proton has an individual charge of either negative or positive, right? Because one's negative and one's positive. Either negative or positive 1 over 6.24 times 10 to the 18, right? This is the number of electrons in a coulomb. So if we want to know the amount of charge in one electron or one proton, we get that value. It should be, I believe, 1.6 times 10 to the negative 19 coulombs. So this is the charge on either an electron or a proton. And this is a special charge because this is like the smallest amount of charge that you could ever have, because there's nothing that has less charge in terms of normal matter anyway, that has less charge than an electron or a proton. So we call this the elementary charge. Elementary charge. We would say that this is, so we say that charge is quantized because you can't have fractions of this charge without having fractions of an electron or fractions of a proton. Some people might be like, but quarks. But I said like normal matter, like the matter that we can, readily sort of study or figure out about or interact with, okay? So yeah, let's leave that with that. So then, how does this play into field strength? Well, if I were to make a field like this, we said that the field is drawn based on the force that a positive test charge would feel. So let's fill in these lines, okay? These electric field lines all point outward from the positive charge, like so, okay? And what we can do is we can bring into this field some amount of charge. It could be positive, or it could be negative. And if it's positive, the force it experiences, which we call Fe, is away. And if it's negative, the force it experiences is the same if these charges are the same size, but it's towards. Okay? So this is called the electric force or static electric force. Okay? So in order to measure field strength, what we would do is we would say the strength of the field, E, is equal to how much force an amount of charge would feel in terms of coulombs. So it's amount of force per coulomb. Okay, the symbols that we have for this are E equals F over Q. Okay, so charge, which has a unit of measurement called a coulomb attached to it, charge is measured in coulombs, and its symbol is Q. Okay, almost done. And the sub E just tells us that it's electric force. Okay, so this is measured in terms of newtons. Force is measured in newtons. We already know that. And charge is measured in coulombs. Now, a coulomb is a very large amount of charge. So in general, we're probably dealing with like micro coulombs. I don't know, we might get a millicoulomb, but I doubt it. Okay, so we're probably more in like micro coulombs. Okay, and if we take this, okay, and we create a little question for ourselves, let's see how we might go about using this. So we could say a field of 10,000 newtons per coulomb exists around a positive sphere. If a 2 millicoulomb charge is placed in the field, at this point, calculate the charge it experiences. I'm sorry, the charge, the force it experiences. My mistake. Okay. Check this out. So we know this, right? We know that the field, strength of the field, is going to be measured in force per amount of charge. We're interested in force, so we could say that we want Fe equals Q times the field strength. So we said Q was 2 microcoulombs, which is, or sorry, 2 millicoulombs, which is 2 times 10 to the negative 3 coulombs, it's millis, times a field strength of 10,000 newtons for every coulomb of charge. Okay, so coulombs would cancel out here and be left in terms of newtons. That's exactly what we want. 3 of those off, we should get 20 newtons. All right, we're going to talk about parallel plates now. You may cheer if you would like. So a parallel plate is basically this. Let's imagine we have 2 rectangles. Oh man, hang on, I'm going to fix my rectangles. Those are ugly rectangles. Rectangles. Oh, I'll put a title in just a sec. Hang on. So let me draw my rectangles. Okay, so this is called parallel plates. So if we charge up these 2 plates with opposite charges, and there's a few ways to do this. One way is pretty simple. You could just like literally hook a battery up to it. This. you're going to get a field created in here, right? How do you know? Because you know that if you took your positive test charge and you placed it anywhere in this field, it would experience a force in this direction. It would be repelled from positive and attracted to negative. So your field would look like this. Oh, for goodness sake. There we go. And interestingly, what this means is the field is the same anywhere inside of this parallel plate system. Okay? So let's say that you know what the field strength is in here, right? Next year in physics, you'll learn a little bit more about like how to deal with this stuff and figure some stuff out on your own. But for right now, we're just interested in already knowing what the field strength is. So the first thing that's important to note about this is that the field is the same strength inside here wherever you go. Field is uniform in the plates. Field is uniform in the plates. Okay. So now let's imagine that you take like a little, I don't know, a little ball of some sort. Let's call it an oil drop. A little wee drop of oil. Okay. And let's say that you're able to negatively charge this little drop of oil. Okay. What forces, and let's say that this little drop of oil is hovering right where it is. So it's hovering there. What forces could we say are acting on this guy? Okay, sure. So you've got electric force acting on it. So you've got some Fe. Which direction does Fe point in this case? Up or down? I think it would be up, right? Because it's attracted to the positive and repelled from the negative. So the electric force would have to be in the upward direction. I don't like that color. I'm going to switch it. Yeah, hang on a sec. Okay. So there's the upward force. But let's say that this is on Earth, right? This is on the surface of Earth. Would there not be another force at work here too? Like, if that's the only force, it's going to accelerate up, and we said it's sitting still in space. Right, so gravity's acting on it too. So if this is sitting still, okay, what that means is Fe upward and Fg downward, adding those together equals 0. So what we could say is 0 equals Fe plus Fg, or in other words, Fe is equal to Fg, but they're in opposite directions. Okay? That's all that negative means, is in opposite directions. Now, can we use this for anything useful? Well, maybe. Let's do an example. Let's put in some numbers. Okay? A 0.5 gram oil drop has a charge equal to that of 15 electrons. In other words, 15 extra electrons have been added to it. Okay? If the drop hovers motionless, what is the field strength? So let's look at how we're going to think about this. So we just look back at our question here, or at our drawing here. We've got the force of gravity pulling down on this thing. We've got the electric force pushing up. Okay. So let's just redraw just the oil droplet. Okay. If we said it had a negative charge, right, it would have to, because it's got the negative plate on the bottom to repel from and the positive on top to attract to. Now let's just see what we can see here. So we've got this Fg down, right? That's gravity pulling down, but we also have this repulsive electric force pushing it back up. So the electric force is going to be equal to Q times the field strength. The force of gravity is going to be equal to the mass of the drop times gravitational field strength. And we know these two values have to be equal, although opposite in direction. So then we could just say Q E should be equal to G. This is the charge. And in this case, that charge is 15 times E, the charge on a single electron. Field strength is what we want. M is the mass of the drop. And G is the gravitational field strength. So G is G field strength. Okay? And we want to isolate for E. This is what we get. mg over Q is equal to E. So mass-wise, I think we said it was 0.5 grams, didn't we? Yep. So 0.5 grams is 5 by 1,000. So 1, 2, 3. 0.0005 kgs times G, 9.81 meters per second squared. Kilogram meters per second squared, we get newtons on the top, okay? Q on the bottom, which is the amount of charge we're talking about, so that's 15 times the charge on a single electron, which is 1.6 times 10 to the negative 19 coulombs on the bottom. This will leave us in terms of kilogram meters per second squared per coulomb or newtons per coulomb, which is exactly the units that we learned were for field strength. So it's just a matter of putting these numbers in our calculator and seeing what we get. So what we get is, we get about 2.04-ish, but I can't really show that many sig figs anyway, so let's leave it at 2.0 times 10 to the 15 newtons for every coulomb, okay? And why is this a really large field? Well, you're never going to get anywhere near an entire newton. You're probably going to be dealing in micro coulombs, I shouldn't say newton. You're not getting anywhere near a coulomb of charge in one place. It's just too much charge. You might get a micro coulomb, but even that is pretty high. Like, that would be a pretty strong field. But anyway, that's how you do a problem like that.